So today, the questions involve op-amps. So 3 questions we'll be doing on op-amps. So I hope everyone has attended already op-amp classes. Op-amps are called operational amplifiers. They are used in circuits mostly to amplify the given signal. So you have 2 input ports and the signal supplied if it is V1, V2 and the output is V0. Now this input ports, the positive side is called the non-inverting terminal and the negative terminal is called inverting terminal. That means whatever voltage we apply in the non-inverting terminal, it will come as it is here. Its polarity will not be reversed. But in the case of an inverting terminal, the image of this V2 will come as minus in the output. That is why these names, non-inverting and inverting terminals. Now if you draw the equivalent circuit of an op-amp, it looks like something like this. So this triangle box is this dotted square which I am drawing. So the circuit will have an input resistance Rin, a voltage source of magnitude AD times VD, the output resistance R out, the input signals V1 and V2 and output V out. So this is the equivalent circuit of a op-amp.
Excuse me, ma'am. Screen not showing.
Oh, okay. Wait a minute. Is it visible now?
Yes, ma'am.
Okay. So, the differential voltage, the input voltages are V1 and V2. So, the potential difference in this terminal, if it is VD, that is this VD of your voltage source. So, VD is given by V1 minus V2. And your output voltage will be AD times VD. Now why we write it like that? Because for an op-amp, the value of Rin will be very high, whereas the value of R out will be very small. For an ideal op-amp, the value of input resistance tends to infinity and the value of output resistance becomes 0. So if that is the case, the same circuit when you redraw, it acts like there is no input. So the input resistance infinity means it acts as an open circuit. So you have your V1, V2 here, your voltage source is AD times VD and your output resistance 0 means it acts as a short circuit. So in other words, your V out is nothing but AD times VD. VD is V1 minus V2. So this is for a case of an ideal operational amplifier. So to solve problems, you should know that this is first fundamental thing which you should know. Now, this is the case of an open loop op-amp. That means You are not connecting the output to the input. There is no electrical connection between them. Now, when you make an electrical connection between the output and input, you have a feedback system. So, feedback systems can be positive feedback or negative feedback. Now, positive feedback means you are taking a part of the output and connecting to the positive terminal of your input, which is your non-inverting terminal. So, this kind of system where you are connecting your output, V out, to the non-inverting terminal of the system is your positive feedback. And the one where you are connecting your output voltage to the negative terminal or inverting terminal is called negative feedback. Now, the positive feedback systems are undesirable systems. They result in an unstable system. So you won't have much control over your output voltage. Why we do feedbacking? Feedbacking we do because we need to have some control over the output. Now, for open loop system, if you see, you don't have any control over the system. Whatever inputs you give, your output will be the gain. AD is called the gain of your system. So, AD times the input is your output. Over the control, AD depends upon the manufacturing of devices used in the op-amp. So, you don't have any direct control over your gain. To get the control only, you will go for feedbacking. Now, there are two types of feedback where this positive feedback results in an unstable system. So, we generally go for negative feedback system where you have control over the output. So, you will have a feedback resistor using which you can control your output voltage. So, there are basic two circuits. One is the inverting op-amp and non-inverting op-amp. These are two basic circuits of an operational amplifier which you should be aware of. How you solve this circuit? By learning how you solve this simple op-amp circuit, you can solve most of the op-amp related problems. So, inverting op-amp and non-inverting op-amp both are negative feedback systems. Both are stable systems. Now, inverting op-amp is the one which is a negative feedback op-amp where you give supply to the inverting terminal. Whereas a non-inverting op-amp is the one where you give supply to the non-inverting terminal. So if I draw the inverting op-amp, I have non-inverting and inverting terminals. I give supply to the non-inverting terminal and the other you will ground. Now, the first and foremost rule for solving an ideal op-amp problem is called the virtual shorting. Now, virtual shorting is nothing but you already learned that for an op-amp, your input resistance is very high. So, ideally it is infinity, but it is very high such that almost no current flows through this circuit. So the current flowing through this is 0 ampere. If you have current through a circuit as 0 ampere, that means the potential difference in that circuit is 0. That means whatever is V1, the same is V2. That means this both V1 and V2 are virtually they are like a short circuit. They are not really short circuited, but virtually V1 is equal to V2 because the current through your R input is negligible. So this is called virtual shorting or virtual ground. We also say virtual ground provided if one terminal is grounded. So virtual ground is a special term for virtual shorting. So if one terminal is grounded, say, that means the other terminal is also having 0 volt. So this is a golden rule while solving op-amp problems, virtual shorting. Now if you take the inverting op-amp, I said inverting op-amp means it is a negative feedback op-amp where you give supply to the inverting terminal. Now if you give supply directly to the inverting terminal and you are shorting the non-inverting terminal, you are basically not following this virtual shorting because this is also Vin. Now this is 0 volt. That means your Vin is equal to 0 volt. Now this cannot happen. So what we will do? We will add the input resistance of your supply. So your supply will have some resistance in it. So that you will add. So you have your supply. So you give the supply through this resistor, which is the input resistance of your supply. Now you can say that this point is 0 volts. So the virtual shorting comes in between the terminals, which is inverting and non-inverting terminals. So now I already mentioned that it is a negative feedback system. Negative feedback system means you will give the feedback to the inverting terminal. So you have a feedback through the inverting terminal, and this is your output. So you have your input and you have your output, and this resistance is your input resistance, whereas this resistance you call it as feedback resistance. So this is your inverting op-amp. Okay, so how to solve an op-amp related problem? So now I will draw it freshly. So that is the reason you always draw a input resistance. So you have V and you have your feedback resistance RF. It is connected to your output, and your non-inverting terminal is grounded. This is your inverting op-amp. Now here the first step, solving means mostly obtaining the ratio V0 by V. Now, as you have learned in your previous classes, you are using Kirchhoff's current law mainly while solving problems related to op-amp. Now, what does KCL say? KCL says that the incoming currents is equal to outgoing currents at a node. So now, you are mixing your Kirchhoff's current law along with your op-amp knowledge. So what do you know about op-amp? You know that the potentials at both these points are same. So if this is 0 volt, this is also 0 volt. That is your first knowledge. Now second knowledge is that because the input impedance is very large, there is no current flowing to the terminals of your op-amp. So, but there may be output current. I never said output current, always it is the input current, because you see at your output you have a voltage source and you have a short circuit because R out is very less. So there will be current I naught will exist, but I in doesn't exist. So I in is 0, whereas I naught may be any value depending upon the load you connect at the output. So now here I naught will be there. Now you see your output is not connected to anything. So to this point your current will not flow because it is open. So the full I naught will go through this, or not. Even if you are connecting your V naught to some load, doesn't matter. So if I am connecting, say I'll take the general case, I am connecting V naught to some load. Still the current, this current, let it be small I. That current will reach here, but it will not flow to the input of your op-amp because of its high resistance. So this whole current I will go to this way. So the current direction may or may not be positive. The direction is according to your wish. If you are giving in the opposite direction, if I am giving like this, then here also it will be like this, here also it will be like this. Just that your KCL equations will become negative. So the current path is like this. This is your current path. So you have two resistors. One end it is V naught. This is RF. This is RI, and this is V in. Now the same current is flowing. Here you have an op-amp, but it doesn't matter because it is 0 ampere. Now this potential is 0 volts. So you can apply Kirchhoff's current law at this 0 potential point. That means potential difference, which is V naught minus 0, divided by resistance, which is RF, is equal to 0 minus V in by RI. That means this current in this branch is V naught minus 0 by RF in the downward direction. Now the same current in the downward direction is going through the remaining branch. So the potential difference is 0 minus V in by Ri. So you have a equation which relates your output voltage and input voltage with just the feedback as well as input resistances. So now your V naught by Rf is equal to minus V in by Ri, or your output by input, which is called the gain of the system, is given by minus Rf by Ri. So you know, in your previous case, you didn't have any control over your output, but here you can vary your feedback resistance or input resistance, and you can vary your output in terms of your input. So this is your inverting op-amp. So this is how you solve op-amp circuits. You assume that the current through going to the op-amp is 0, the potentials at both terminals of the op-amp are same, and if you do that, you can just solve the remaining circuit by using Kirchhoff's current law. Now let us take what is a non-inverting op-amp. So as I said before, non-inverting op-amp is also non-inverting op-amp is also a negative feedback op-amp where you give the supply to the non-inverting terminal. So you have an op-amp plus minus. When you give supply to one terminal, you will short the other terminal. So I am giving supply to your positive terminal, and the negative terminal I cannot short because your negative terminal is your non-inverting terminal. The negative terminal is your inverting terminal. Now I am giving feedback to it, right? So I am giving a feedback V naught. Now if you see, if I do like this, there is no current through this path because it is the input to the op-amp, and also this will also become V in. You cannot write any KCL equation because there is no current flowing. This current is 0, this current is 0, the current through this path will also be 0. So you will add another resistor here. Let it be R2 and let this be R1. So this is circuit for a non-inverting op-amp. So these both are conventional circuits. So your non-inverting op-amp looks like this and your inverting op-amp looks like this. So if you want to solve your non-inverting op-amp, solving means, I repeat, you getting the output by input equation. So it is a negative feedback system where you give the supply to the non-inverting terminal. So this is your non-inverting op-amp. Now I can approach this in 0 ampere. So this current is also 0 ampere. Now this potential is same as your V in. Now you have your output current. You have your output current I naught. Output current is split into two parts. One will go to the load. If there is no load, no current will go. It goes directly to the feedback resistors. So say I am connecting a load here. So some part of I naught will go through the load. The other part, say small I, will go through your R1. Now this current cannot enter your op-amp, but so this current will go through R2. So I can apply Kirchhoff's current law at this node. So the current is in this direction. So when you consider R1, the equation of that current is V naught minus V in by R1. That means V naught is a potential at this point minus V in, because current is flowing in this direction. So V naught minus V in by R1 is this current. That is same as this current. Now what is this current? This current is V in minus 0 by R2. So that current is V in minus 0 by R2. So your V naught by R1 minus V in by R1 is equal to V in by R2, or V naught by R1 is equal to V in into 1 by R1 plus 1 by R2, or your V naught by V in became 1 plus R1 by R2. So this is the equation of your non-inverting op-amp. So you see, For inverting op amp, your V naught by V in was minus RF by Rin. But in this case, it became like this. So in inverting op amp, your output will have a negative sign, which means your output will be 180-degree phase shifted from your input. But in non-inverting op amp, the polarity will be same and you can control the gain using R1 and R2. So I hope you learned how to solve equations involving op amps, a simple circuit. Now we are going to some advanced version. So this is the first problem. Please go through the problem. I'll give you 5 minutes to solve it yourself. So let us begin the discussion. So in the given problem, determine the percentage error from the ideal gain in the figure above. Ideal gain refers to V0 by Vn with an ideal op-amp. Percentage error is defined as 100 times V0 by Vn ideal minus V0 by Vn. So sorry. So first let us find out what is the ideal gain. So ideal gain means when this op-amp is acting as an ideal op-amp. That means you have the concept of virtual ground. Now I've already explained the circuit before. This is a non-inverting op-amp, right? Which we discussed just before. So you have a negative feedback and you are giving supply to the non-inverting terminal. So either you can directly apply the equation which you solved before or you can solve it yourself. So an ideal gain, when you are considering an ideal op-amp, your non-inverting terminal voltage and inverting terminal voltage are same. So this is also V in. That means this is your V in. Now you can apply your Kirchhoff's current law following this path. If you do that, you get V0 minus Vin by 3 is equal to Vin minus 0 by 1. That means V0 minus Vin is 3 times Vin, or 4 Vin is equal to V0, or V0 by Vin is equal to 4. So this is what you got before. You got 1 plus R1 by R2, where R1 in your case is 3. So here it is 1 plus 3 by 1, which is 4. So you got the same answer. So this is a non-inverting op-amp. So this is your ideal gain. So your ideal gain is this, 4. Now you, in the actual case, you have to find your V0 by Vn in your actual case. So then you can redraw the circuit. So this is your Vn. This is your V out. Now you know that. Now here you cannot apply your virtual ground. You have to give another name for this. This is V2. So in practical case, you cannot equate Vi and Vi. The virtual shorting or virtual ground concept you use in the ideal case. So here, I am assuming that your inverting terminal voltage is V2. Now we know that in ideal case, your V out is nothing but AD, which is your open loop gain times Vi minus V2. Now AD is already given in the question. AD is 396. So your AD is 396. Now you have to find what is V2. V2 we don't know. Now you have to express V2 in terms of V0 or Vi. Now you see, even though you are not applying the virtual ground concept, you can still say that the current entering is very much less. That means this current, this is the same current flowing, or you can apply your voltage division rule. So you have a branch, this potential is V2, this is V0, this is 3K and this is 1K. That means your V2 is V0 times 1K divided by 1K plus 3K, or your V2 is V0 by 4. Now if you substitute in this equation, your V naught is AD times V in minus V2 is also V naught by 4. Now your AD is 396. 396 minus VI into VI minus V naught by 4 is V naught. Now if you take this here and there, you get V naught by V in. If you solve this, it comes out to be 3.96. So you have your V naught by V in ideal as 4 and non-ideal as 3.96. So now you can find the percentage error. The percentage error is 100 times. Given in the question, the equation is V naught by V in ideal minus V naught by V in. So here it becomes 4 minus 3.96 or it becomes 4 percentage. This much percentage it is. So this is the answer to your question. You can stop me and ask if there is any doubts. This is your next question. Kindly go through it. We'll have discuss it in 5 minutes. So you are asked to determine the negative terminal of the op-amp in the figure above so that it is in negative feedback. So you are given two terminals AB, you don't know which is your positive and which is your negative, which is your non-inverting and which is your inverting terminals, you don't know. So you are asked to determine which is which so that it acts as a negative feedback circuit. So the usual procedure which we follow to determine the signs of the op-amp for negative feedback is first you should remove the op-amp, or you have to replace the op-amp with its equivalent circuit where you give its output as a test voltage V test. While doing this, if there are any other independent sources in the circuit, you have to null them. Nulling means you have to replace the independent sources with its equivalent internal impedance, which we know that for a voltage source, the equivalent impedance internal circuit becomes short. Whereas for a current source, you have to replace it with an open circuit. So this is the way you should do when other independent sources are there. Now, the third step is you have your op-amp. The input voltage to that op-amp is VAB. So you will write VAB in terms of your test voltage V test in the form VAB is equal to alpha times V test. So the op-amp is here. Now I am replacing. So we don't know which is plus and which is minus. So you are naming it as AB. You are naming it as AB. And this potential is VA and this potential is VB. Now you draw it. You make it VA here and VB here. And this part you will give your test voltage. So this is your V out. So you will replace this whole part in the circuit by this, by replacing the independent sources with its equivalent circuit. Once you do that, you will get your VA minus VB, which is nothing but your VAB, in terms of some constant alpha times V test. Now the fourth part is checking for alpha. If alpha is greater than 0, then your A is the inverting terminal and your B is the non-inverting terminal. If it is in the other way, if alpha is less than 0, then your A is non-inverting and B is inverting. So this is the process of observing, checking which terminal is what in a negative feedback system. So in this problem, we will solve this problem using the similar approach. So I will draw the equivalent part. So I'll open this. Now this is my A and this is my B. So this is VA and this is VB. Now this part is connected through a 6 ohm kilo ohm resistor to your output, where output I am replacing with a test supply source. And here you have another 4 kilo ohm. So this is your equivalent circuit. So now, since there are no other independent sources in the circuit, we don't have to replace anything. So now I have to find what is my VAB in terms of V test. For that, you have to make use of your Kirchhoff's current law, which we already discussed. So if this is V test, now the point V naught is same as V test. So first you can take one current path. So this current will reach here. You know that it is open circuit, so current will not flow to VB. So this current will go like this. So if this direction I take this like this, so you have two resistors. One part is V test, the middle is VB, and the other part end is ground. And this is your 4 kilo ohm and this is your 1 kilo ohm. I'm going to apply Kirchhoff's current law. So the current from V test to VB is V test minus VB by 4. That is the same current which flows from VB to ground. That makes my V test minus VB is equal to 4 VB, or 5 VB is equal to V test, which gives my VB as V test by 5. So this is my first equation. Now the second equation you will get if you consider this path for current. So you have two resistor, one part grounded, the other part is your V test. Here it is VA and it is going through 6 and 2. So this is 6K and this is 2K. So the current from V test to VA is V test minus VA by 6. It is same as the current from VA to ground. So this is VA minus 0 by 2. So this becomes V test minus VA is equal to 3 times VA, or 4 VA is equal to V test, or your VA is V test by 4. This is equation number 2. So you have your VA as V test by 4 and your VB as V test by 5. That means your VAB is VA minus VB, which is V test by 4 minus V test by 5. So this is V test into 1 by 4 minus 1 by 5, which comes out to be 1 by 20 times V test. So your alpha is 1 by 20, which is greater than 0. That means your terminal A is inverting and your terminal B is non-inverting. So if alpha is greater than 0, your terminal A is inverting. So in the given question, determine the negative terminal of the op amp. So the negative terminal is your inverting terminal. So that is A. So if there are no doubts, we'll move on to the next problem. Please go through this problem. You have 5 minutes to think. in the circuit. Determine the coefficients alpha and beta in the expression for the output V naught. So you have two op-amps. So I will redraw the circuit so that we can mark on the op-amps and proceed. So this is your circuit. You are asked to express V naught in terms of V1 and V2, where V naught is alpha V1 plus beta V2. So how to write this? So let us start with the basics. Whatever we know, let us apply on the circuit. We know that these are ideal op-amps, so we can apply the virtual short concept. So this point, the voltage is V1 because one side is ground, other side is V1. That means at this point also that is V1. That means this point is also V1. Now this point we don't know, that is the output voltage of the second op-amp. So let it be V01. Now considering the inputs of your second op-amp, this point is V2. That means this point is also V2. We don't know whether it is inverting or non-inverting terminals, but we know that virtual short exists. So this is also V2. Now this is already given V0. Now what is the second thing you know? That is, there is no current here in the input terminals of an op-amp. There is no current, but the output terminal can have current. So let this current be I0. Since your output is open, the same current I0 will flow through here. So I0 will reach here. Now here, because no current goes to the input of your op-amp, the same current is also I0. Now this comes here, the I0. Now this op-amp may have an output current, we don't know. Let it be I1. If that is I1, then here I0 plus I1 will flow, Kirchhoff's current law. Now this I0 plus I1 will enter here, and you know that no current flows to the input of the op-amp, so this whole I0 plus I1 will flow through this. Why I am writing this current names? Because you can identify which is the paths where same currents are flowing. So the first path where the same currents are flowing is this path. So in the yellow colored path, the currents are same. So you can apply Kirchhoff's current law. If I redraw the circuit, this is your V0, this is your 2K, this point is your V2. Now this is your 8K and this point is your V01. So this is your one branch. You can directly apply your Kirchhoff's current law. So this current is I0 and this current is also I0. Now which is the second branch? Now the second branch is I0 plus I1. So the I0 plus I1 flows through here. So this is your second branch. So the second branch is 2 resistors. One part is grounded, the other part is V01. and middle is V1 and both are 1K. So let us apply in the second branch your KCL first. So the current flowing is same. So the current flowing from V01 to V1 with 1 kilo ohm in between is V01 minus V1 by 1. The same current, which is equal to, flows from V1 to ground through 1 kilo ohm resistor. So this is V1 minus 0 by 1. So this gives us V01 is equal to 2V1. So in the second circuit, I can directly replace this V01 with 2V1. Now let us write the second branch KCL. I0 flows from V0 to V2 through 2K. So the I0 is V0 minus V2 by 2. That same I0 flows from V2 to V01. So V2 to V01 is 2V1 by 8. So you can cut this 4. So you have V0, 4V0 minus 4V2 is equal to V2 minus 2V1. That means my V0 becomes 5V2 minus 2V1 whole by 4. This you took outside, so 4 plus 1 became 5 minus 2V1 the whole divided by 4. So your V0 became 5 by 4. It is 1.25 V2 minus 1 by 2 which is 0.5 V1. So that is minus 0.5 V1 plus 1.25 V2 is your V0 which is asked in the question. So your alpha is minus 0.5 and your beta is 1.25. So this is how you solve these questions. You will identify that the current entering the branches are 0. So current in the input of op-amp, you make it 0. Next is you apply virtual short concept and then you identify the branches which carries same current. Once you identify the branches, you just have to apply Kirchhoff's current law. So follow these 4 steps, you will be able to solve most of the problems on op-amp. So in this question, your value of alpha is minus 0.5. So you're asked to round off the fractional answers to 2 decimal places. So this is minus 0.50 and this is 1.25, 2 decimal places. Is there any doubt? Please ask. So with this question, we come to the end of today's session. So almost all the problems in your op-amp practice problems are solved in this session. So you can solve the assignment questions which is similar to these problems and submit it by time. So thank you all. Meet you next Tuesday.